All right, so we're going to talk about gases, okay? This is the first half of the gas unit, I guess. We'll go slides, I think, about 1 through 18 or 1 through 20. Um, so here we go. All right, now a lot of this first presentation is going to be some review from last year. We're going to talk about kinetic molecular theory. We're going to look at Charles' law and Boyle's law. We're going to look at Avogadro's law. We're also going to expand that idea just a little bit. So, just a couple characteristics of gases that are important that we kind of recap. Number one, all gases physically, anyway, are pretty similar, okay? They're mostly non-metallic elements. They have low molar masses. You know, our diatomic gases are included there, like, H2 and N2 and O2, those kind of things. They expand to fill their containers, which means they have an indefinite volume. They are highly compressible, right? Easily, squeezed into a small space. They have a really, really, really low density. So, to kind of picture the low density, if you have the volume of air in a breath, all right, about 0.1% of that volume is occupied by molecules or atoms. The rest of it's just empty space. The same volume as a liquid, about 70% would be occupied by atoms. So there is extremely low density of atoms in the gas. If you have a bunch of gases together and they don't react, then they'll form a homogeneous mixture. They'll form a solution, like air is a homogeneous mixture of many gases. Okay, so a couple things to recap. When we want to define gases, we look at their temperature, and we use Kelvin in order to do that. We look at their pressure. We'll talk a lot about the pressure units here shortly. We'll go back. We'll look at their volume, and we'll look at the amount of gases that's there in moles. We've kind of already talked about temperature, pressure, and volume pretty heavily in the first year of chemistry. But just to kind of recap for you, temperature will be in Kelvin, and Kelvin is going to be degrees Celsius plus 273.15. You can leave off the 0.15 for, the 99% of calculations. Pressure we'll look at in just a second. Volume is, length times width times height. Height, okay. That's going to give us our volume. It's going to be some kind of, cubed unit. Remember that 1 milliliter equals 1 cubic centimeter, which is the same thing as a cc. All right, so 1 milliliter, 1 cubic centimeter, 1 cc, all the same thing. Obviously, the amount of gas is expressed in moles. We know moles has to do with Avogadro's number, right? 1 mole is 6.022 times 10 to the 23rd atoms, right, or molecules, But let's look at pressure a little closer. Now, pressure is force, okay? And we define pressure as force divided by area. So atmospheric pressure is the weight of air in a singular unit of area from the top of the atmosphere all the way to the bottom. So something kind of, I guess, interesting about pressure. We calculate, the gravitational force using this pressure, right, the 9.8 meters per second. And you can get there through these pieces of information right here, the cross-sectional area of 1 meter square. That much air weighs 10 to the 4th kilograms. That's what's pressing down on you at sea level, right? In a cross-section of 3 feet by 3 feet, right, 1 meter square, you have 10 to the 4th kilograms pushing down on you. That's a pretty fair amount of weight, right? Pretty fair amount of mass. That pressure is measured in pascals. That's 1 Newton per meter squared. That's the SI unit for pressure, the pascal. It's also measured in bar. A bar is 10 to the 5th pascals or 100 kilopascals. It's a useful conversion to know right there. 1 bar is 100 kilopascals. We also measure measure pressure using millimeters of mercury, mmHg, or torr. Remember, they're the same thing, and they are derived from the difference in heights in those mercury barometers. This is a barometer right here, one of the original barometers. You have a big puddle of mercury with an open face top, and you have a vacuum tube, so there's no air or anything in that tube. And the pressure of the atmosphere pushing down on this tube makes the mercury climb, and they're just measuring the height right there in millimeters of mercury. An atmosphere is equal to, let me move this out of the way here. There we go. 760 torr, 700 millimeters of mercury, right? Same unit. It's equal to 101.325 kPa. We usually just round it to 101.3, and that also equals 14.7 psi. Now, hopefully we can take those conversions and we can do some math with those, right? So like if I want to convert atmospheres to torr, I know that one atmosphere is 760 torr. Atmospheres cancels. I'm left with torr. 0.357 times 760 is 271 torr. All right, if I want to go PSI to ATM, well, 14.7 PSI is the same thing as one atmosphere. PSI cancels, right? Pounds per square inch is what that stands for. And I get 6.22 atmospheres, okay? 91.5 divided by 14.7. If I want to do kPa to torr, right, I need to go through atmosphere, so it's going to be a double bracket problem. So there's 101.3 kPa in an atmosphere, and one atmosphere is 760 torr. Okay, so 147.2 divided by 101.3 times 760 is 1,104 torr. So that's how we use those. Now, there are a lot of different ways that we might end up measuring gas in the lab. One is called a manometer, not a manometer, it's a manometer. And we use it to measure the difference in atmospheric pressure and the pressure of gas in a sealed vessel. So the manometer measures gas that we're capturing here. And what you do is the pressure of the gas equals the pressure of the atmosphere plus, all right, this height, all right, this movement against that pressure, okay? So the manometer starts out usually even, in which case the pH would be 0, right? And then as this gas pushes up the tube, all right, it moves the mercury out of the way. And so this change becomes from the low point on the left side of the manometer to the high point on the right side of the manometer becomes our H that we're looking for there. Now, standard pressure, or STP, that we talked about last year, right? Standard pressure. So when you see the term STP, we're talking about standard. All right. Oh, come on, pen. What happened to my pen? There we go. Standard pressure, okay, is the normal atmospheric pressure at sea level. That's one atmosphere. Makes sense, right? At sea level, you have the whole atmosphere above you. That's equal to 760 torr, or 760 millimeters of mercury, or 101.3 kilopascals, okay? Some laws from last year that I hope we're still familiar with, right? Boyle's law says that a volume of fixed quantity of gas at a constant temperature is going to be inversely proportional to the pressure. So as the pressure goes up, the volume goes down. As the volume increases, we would expect the pressure to decrease, okay? Those are, inverse relationships, okay? When we graph Boyle's law, which this is probably more important than the other slide, just so you know, pressure times volume is a constant. So if we compare the two, you can go P1 V1 equals P2 V2. That's Boyle's law. If we graph volume versus pressure, it's not linear, though. We get this one here. We have volume versus pressure, okay? That's because you can only compress a gas so much, right? It's not going to compress all the way down to 0. That would be, mass taking up 0 volume. That's not going to work. So you won't get it to work there. However, if you graph volume versus the inverse of pressure, 1 over P, you do get a linear relationship. That's a very useful thing for making some comparisons. From this, right, because we're getting a linear relationship, we can say that volume, all right, is proportional. That little alpha symbol there means is proportional to 1 over pressure, to the inverse of pressure. So volume is proportional to the inverse of pressure. Now, Charles' law tells us that the volume of a gas is directly proportional to absolute temperature. So we can see in this picture, all right, if I heat the balloon, all right, the volume is going to increase. If I cool the balloon, the volume is going to decrease, all right? And that makes sense, right? The cooler the gas, the slower the molecules are moving, the less pressure they can exert on the outside of the balloon, so the balloon deflates. Now, we don't have to do the inverse of anything here to look at the mathematical relationships for Charles' law. Volume is just proportional to temperature, right? So we say that volume is proportional to temperature. When we look at Charles' law, we see that volume 1 divided by temperature 1 is equal to volume 2 divided by temperature 2. And I can look at this linear, volume here, and linear graph here, and I can make an extrapolation. Now, this is pretty cool. We can see here that at negative 273 Celsius, we reach 0 volume. Now, we'll talk more about absolute zero later, but there is a lot of, I'm not going to say argument, we'll say discussion in the scientific community as to whether or not you can actually get something all the way down to absolute zero. Now, I don't have a PhD in physics, but I can read a graph, and in my opinion, I would say no. Now, they've gotten very, very, very close, within, hundredths of a degree. But this graph tells me that when you get to absolute zero, your mass is no longer occupying any volume. And that, to me, seems to break, some basic laws of physics. Like, if something is matter, it has to have mass and volume. So if I try to cool matter down to absolute zero, the volume is going to be equal to 0. That doesn't make any sense to me. Now, I would love to be proven wrong. I really hope they do get something to absolute 0. That would be wild. But this graph, one, it identifies where absolute 0 is because it's the point at which that volume line becomes 0. And it also shows us the volume and temperature relationship for an ideal gas. But it's kind of interesting to just, extrapolate that over into the absolute 0 conversation. When we do thermochemistry, which is chapter 5 and chapter 19, thermodynamics, we'll talk a lot more about absolute 0. Avogadro's law is something that we covered briefly last year. We didn't go into a lot of depth with Avogadro's law. We did learn that it was V1 over N1 equals V2 over N2. We solved it just like Charles and Boyle's law, but we didn't really take it much further. So some things that come out of Avogadro's law: 1 mole of gas is going to occupy 22.4 liters. Okay, that's important. Doesn't matter what the gas is. Okay, it's going to occupy 22.4 liters. Now that lets you do some interesting things. It lets you mass the gas if you keep the pressure and the temperature and the number of gas molecules and the volume the same. So we can see that helium at 1 atmosphere, 0 degrees Celsius, right, at STP, so there's standard pressure, there's standard temperature, 1 mole is going to equal 4 grams. Interesting. N2, right, nitrogen, diatomic nitrogen is going to be 28 grams. CH4, right, methane would be 16 grams, roughly. Okay, so that's Avogadro's law. If we were to go out and graph this, all right, we would find that the volume is going to go up as the number of moles go up. And so we can say that volume is proportionate to the number of moles. Now, when you take these 3 things together, these 3 proportional statements, and you combine them, we can find that volume is proportionate to N times T over P. In order to make it an equality, we're going to add a proportionality constant. We call it R. and we're going to get the ideal gas equation, PV equals nRT. And R is what lets us take that little proportionality statement, and R makes it an equal sign. Okay, we want to make it an equality. Well, what is R? R is a lot of things. Okay, the big thing about R is this little fact right here. The units of R must agree with the units in the problem. Now, the product of PV is a unit of energy, and like impulse. And we'll look more at that when we do Chapter 5 and Chapter 19. And that's when we'll see these two values for R right there, joules per mole Kelvin especially. Last year, after we went on break, we did some videos on specific heat, which I'm sure you all watched. And the specific heat uses that R value, and we'll use that again this year. The R value you're probably most familiar with is this one right here, which last year we usually rounded to 0.0821. Okay, liters times atmospheres over mole Kelvin. Remember that we can write this unit as an inverse. So we could say 0.0821 liter atmosphere times mole inverse times Kelvin inverse. You're going to see that a lot in some of the work that I do in later videos. This inverse, right, that -1 exponent tells you that the mole and the Kelvin goes on the bottom of our units there as a fraction. So really we have liter atmospheres, oh, come on, pen, there we go, over mole Kelvin. But this is a more convenient way to write it in parentheses on a single line sheet of paper. Now, you can take this equation and you can start to incorporate some substitution algebra and use it to solve for density. So if you divide both sides of the ideal gas equation by V and then RT, you'll get N over V equals P over RT. We know that moles times molecular mass gives you the mass, so I want to get rid of this N right here. And so I know that N equals the molar mass times the mass, so I can plug that into my equation. I get mass right there, I get the molar mass right there, and I can find that mass divided by volume equals PM over RT. We know that mass divided by volume is density, so density equals PM over RT. Density equals P, fancy M, right, molar mass of a gas over RT. Lots of different ways you can remember that. I'm sure you remember some from last year. You can also solve the density of a molar mass equation, right? Density equals PM over RT can be solved for molar mass. So let's do that. Density equals PM over RT. I can multiply both sides by RT. So I have P fancy M equals D times R times T, divide by, divide by P. We're looking for molar mass. There we go. Oh, come on, pen. What's going on here? There we go. P on both sides. So I get the molar mass of a gas equals dRT over P, which is not RP. What is wrong with my pen right now? Oh my goodness. dRT over P. There we go. So the molar mass of the gas, this is affectionately referred to as the dirty P equation, dRT over P, dirty P. That's the molar mass of a gas, okay? So just a little recap here. The density and molar mass, you just need to know molar mass, all right, molecular mass, pressure, and temperature to find density of a gas. That's a really useful thing. It's a common thing that we'll see in AP Chem. If we know the mass, the volume, and the temperature, we can always find the molar mass, okay? And we use this equation here, all right, in order to do that, okay? Make sure, all right, I'm going to kind of backtrack some here. This is the last slide for this lecture. Make sure you know the density equation of a gas. Make sure you know that one, all right? If you know density, you can solve for molar mass. Make sure that you have This equation stuck in the back of your head somewhere. Make sure you know this R value, all right, because those are the two that we're going to use the most. For the purposes of the SI unit, there's the SI unit for R. All right. Meters cubed over times pascals over mole Kelvin. That's better than liters over atmospheres, right? These are not the SI units there. All right. So that's it for the first part of the gas lecture. Let me know if you have any questions. All right. I'll be glad to give you a hand.